Okay. We have exam 1 on Friday, right?
Yeah. I thought it was next Wednesday.
We don't have class on Tuesdays, so that much I know. Exam 1. And the topics are up through principal stresses. So let's go through a couple of these assignment problems today that the solutions aren't posted yet for. How many people in here are going to have to do the test, calculate the eigenvalues by hand? Oh.
You can rent a calculator.
Yeah, from the library.
I might be able to get one if I can figure out my sister's.
Okay. Well, it'll be possible to do by hand. I'll make sure that it's only quadratics you have to solve, but the test will definitely be a lot shorter for the people who can just punch things into a calculator. So today, before we go on to the next stuff, I just want to spend the day doing principal stress calculations, maximum shear calculations. Yes.
So when you ask for, like, give the corresponding coordinate system,
Mm-hmm.
that's always just asking for, like, the 3 normal vectors.
Yeah. But remember that you have to choose which one is your x and which one is your y and which one is your z, and those have to satisfy I cross j equals k, I cross k equals negative j, and j cross k equals I.
Can you elaborate on that a little bit?
Yeah.
Oh, quick question.
Yes.
Our calculator sort of sorts it out for us, doesn't it?
Yes.
Okay.
The calculator does. You have to, if you're driving manual, you got to think about that kind of stuff.
Oh, yeah.
So they're driving automatics.
Yeah, exactly.
Okay, at least I won't burn out my brakes while driving out.
That's true. But you can burn out just don't burn out the clutch while you're starting on a hill. It's really easy to do. Starting on a hill. Yeah.
I don't know how to drive manual.
I don't know what these sounds are. Would you put on your clutch?
I don't know.
Just keeping it right at that spot so you don't roll
Yeah.
back without using the handbrake. Right.
I might have to.
Okay. Okay, so first example. This is let's do number 4. So the stress tensor is 0, 0, 0, 0, 1.33975. I just came up with these off the top of my head. 0, 5, 18.6603. This is February 3rd. Why did I write 2? February 3rd. And this is megapascals. So A is just drawing the stress element. Let's skip that. What are the principal stresses and the corresponding coordinate system axes? Okay, so do that. Okay, so you get eigenvalues the principal stresses are 20, 0, and 0. And the corresponding axes are 0, 0.259, 0.966, and then 0, positive 0.966, negative 0.259. Makes sense. And then 100. A TI-89 gives them in this order, and then you can just use this order as X, Y, and Z. It's very nice. So
I'm trying to clarify when you can. Sometimes we need like a very small number, right? And then now
yeah, when did those very small numbers are really only strains. So if you have strains, you can get those times 10 to the minus 5 and 10 to the minus 6. You usually will. But for stresses, even in megapascals, ones that low are negligible. Okay, so how do you know that this is an acceptable coordinate system? So right-handed coordinate system requirements. I cross J has to be equal to K. I cross K has to be equal to negative J, because Y always has to be the difficult one. And then J cross K has to be equal to I. So let's test it out. So 0, 0.259, 0.966 crossed with 0, 0.966, negative 0.259. No. Oh. Equals 1. Oh, no. That doesn't work. Did I? Well, I guess it's good we checked. This is equal to negative 100.
Your x component have a 0 in the x. And your z.
They're all jumbled around. They're all over the place. Yep.
So what we're doing right now is
Checking to make sure that what we chose as X, Y, and Z correspond to a right-handed coordinate system. If it doesn't, you can't use it.
So by switching around our values for X, Y, and Z, we can...
Yeah, or by making the axes point in the opposite direction. So let's try this. So yeah, let's take this, use that to say, okay, our z-axis is negative. And now let's try the other two. Maybe it'll work. My confidence is took a little hit there. Not gonna lie. So
So we can just go back and call that negative.
yeah, right. Yep. Now I crossed with K 0.259, 0.259, 0.966 crossed with negative 100 is equal to 0, negative 0.966, positive 0.259, which is opposite of I, so, opposite of J, so that's good. And then the last one, when we take J and cross it with K, 0.966, negative 0.259, crossed with negative 100. Hopefully that'll give us I. We get 0.259, 0.966. Okay, well, I guess we have to check those. I don't know how I never noticed that before. I guess we got to check those. Anyone have any questions about how I did that checking of the coordinate axes? Follow the idea there? Okay. So now anyways we have a coordinate system where the x-axis is, so let's draw it.
You said notice we have to check those. We're doing that right now?
That's what we just did.
That's what we just did.
Yeah.
Changing the negative.
Yeah, changing the orientation of possibly one of those axes to make it a right-handed system. Okay, so now in the old coordinate system, let's draw the orientation of the new coordinate system. So our new x-axis, and here. So here's the old coordinate system. And let's say this is y and this is z. And that means that x is coming out towards us. That's the old coordinate system. 0.259, 0.966. So there's our new x-axis. Our new y-axis is 0.966, negative 0.259. And our new z-axis is into the page.
Have you broken it down like that yet?
Yeah.
Okay, I just never got it.
Yeah, you weren't listening. That's what happened.
It was
True. Yeah, exactly. Okay, so now that we have, and in this coordinate system, the principal stress tensor then is just x, y, z. It's the eigenvalues corresponding to the x, y, and z axes in the new coordinate system. So it's just 20, 0, 0 with no shears. Okay. So that part, well, it's always going to be x normal stress, y normal stress, z normal stress in that order. So where your principal stresses fall in this is determined by which of those eigenvectors you make your x-axis, your y-axis, and your z-axis. Now, part D. Yep.
So you decided what the x, y, and z was for us just by giving us this particular stress tensor, right?
I decided it up here. I just made this x, made this y, made this z. And then when I did the check to show you that it worked out, it didn't work out, and we had to make one change to it. But I'd already decided what was going to be my x, y, and z, and each one of these corresponds to one of those principal stresses. And so once you choose the axes, you've also chosen the order of those diagonal elements. Any other questions about that relationship? Yep.
It's still not clear how you got the new coordinate, this guy.
I just went,
The numbers.
yeah. Okay, so I drew out, so the interesting stuff with these axes was going on in the YZ plane, right? So I drew the old YZ plane in red. And then I just sketched out those axis vectors. We have a small positive x component and a big positive y, a small positive y component and a big positive z component. So for the x-axis, and so that's this. Then for the y-axis, we had a big positive y component and a small negative z component. So that's this.
Okay.
Like basically you're just plotting, you're plotting these points.
And you're drawing a Z right in the middle, right where X was, or is Z moved?
No, it's right in the middle. It's right in the middle.
Okay.
I just drew it over there so you could see that those are in opposite directions. I mean, so all I'm doing is plotting, if you just think of these as the coordinates of the head of the vector, I'm just plotting these points. Okay, so now calculate the Voigt strain for the principal stress tensor. The Voigt strain in this principal coordinate system is 1.0 times 10 to the minus 10. So yeah, these are tiny, but you can't neglect these. Negative 3 times 10 to the minus 11. Negative 3 times 10 to the minus 11. And then no shears. And that's what you'll always get when you calculate the shears that go along with a principal stress. These two are the Poisson's effect. Those are the those are the contractions in the off axes that go along with stretching along the main axis. Okay, so now let's do this two ways. So first, what really is more often important is just figuring out the magnitude of the maximum shear. So what's the maximum shear stress? Well, to get that, that's equal to the max principal stress minus the minimum principal stress divided by 2. The max is 20. The min is 0. So we have 20 divided by 2 equals 10 megapascals. And so now calculate a stress tensor with maximum shear. So you're going to do this as a rotation, and you should get somewhere shear values that are either plus or minus 10 megapascals. Okay, so your principal stress tensor is 20, 0, 0 with no shears. Oh, you know what? I just realized that when we did the strain, I think I entered the I think I entered it just as 20s. So this is times 10 to the 6 pascals. You know what I mean? And so these strains are really times 10 to the 6. Mega strains. Yeah, right. Mega strain. Okay. And the rotation matrix I chose was about the z-axis. But you could do it about the y-axis too, and you could go plus or minus 45 degrees. They'd all give you different answers, but they'd tell the same overall story. And then your stress tensor with max shear is equal to Q times the principal stress times Q transpose. And I got 10, negative 10, 0, negative 10, 10, 0, 0, 0, 0.
And the only thing that really counts there is the shear. Like you're not interested
Right.
in that at all.
Yeah, you don't tend to be interested in anything except the shear stress there.
And what axis was that rotated about?
I did it about Z.
And so if you did it about y, it would just.
Yeah, I guess it would probably be 10, 0, 10 or negative 10.
Okay. Like 10 in the corners.
Yeah,
Okay.
and 0 is on the main row and column, middle.
In this case, do we really care about the negatives?
Usually you don't care about them. And so usually the only thing you would need this most of the time, for what you need that maximum shear for, you could just use this algebra formula, calculate what it is. But there are always times where you want to know the full state of stress in a coordinate system. And when you would want that and when you wouldn't has a lot to do with just the kind of material it is, because different materials have different likelihoods of failing in tension and compression and shear. So if you had one that you knew was going to fail in shear, like bone in a compression fracture, or even some metals in pure compression, this algebra formula would be enough. Largely, I'm having you do this stuff just to try to make sense out of how it works, rotating these coordinate systems and re-expressing the stress tensors and stuff. Okay, if you calculated the strain for this stress tensor, would you have any shear stresses? Yeah, anytime you have shear strains, anytime you have shear stresses, you have corresponding shear strains. So the way I have it, you would have a shear strain in the XY position. Any other questions? Okay, let's stop there. And next time I'll